Hello everyone. Welcome to the next webinar in 12D's training webinar series. My name is Lisa Stewart and I'm the Marketing and Communications Coordinator at 12D Solutions. 12D's training webinars showcase common industry challenges, taking a close look at industry best practices and how these can be implemented using 12D products. The aim of these webinars is to upskill 12D users and broaden their understanding of the capabilities of 12D products. We run these webinars regularly and record them for posting through our website and on YouTube. The first 42 webinars from this training series, as well as the webinars from our Industry Solutions series, are available on our YouTube channels if you missed those. During today's live presentation, you'll be able to type your questions along the way, as shown on the screen, and we'll answer as many as possible throughout the webinar. At the end, I'll also read out some of your questions to the presenter for his insights if there's time. Today's webinar, Directional Kerb Ramps, will be presented by David Owens, who has over 30 years of experience in design of civil infrastructure, including roads, drains, parks, sports fields and landfill for Brisbane City Council, as well as more than 18 years of experience as a 12D user and 10 years as a 12D trainer. Directional kerb ramps have always been a thorn in the 12D modeller's side. They're manually intensive to model, so they're often left to the last minute as no one enjoys drawing these things again and again. Having felt these frustrations too many times in previous jobs, our presenter set out to find a way to build up the kerb ramp using a combination of the Apply MTF function and computated super-alignments, so he could draw them once and then get them to update via a chain should the horizontal or vertical position need to change. Over to you, David.
Okay, thank you very much, Lisa. Yeah, so on the screen there I've got the the offending article, the thing that has been giving me grief over the years. Just a little extract from our standard drawing here at Brisbane Council. So the problem with these has always been that chicken and egg problem, that you're trying to make sure you don't exceed maximum grades, they keep within limits of horizontal position, and also the fact that they're just at a horrible angle compared to the curb itself. So trying to deal with it in simple modifiers is just gets too hard, basically. And in today's environment where everybody wants, 3D fly-throughs and all these sorts of things quite early in the program, you've really got to have these things in for the fly-through models, those 3D models, to actually look correct. So anyway, to model with this thing, as Lisa sort of pointed out, I'm just going to use some super-alignment, computated super-alignments, beg your pardon, to try and work my way through that sort of chicken and egg issue. And using the apply function, but maybe just with a few little sort of variations that you may not have sort of thought about in the past. Okay, so let's get into it. So what I've got here is simple little curb return alignment, nothing particularly outrageous about it, pretty standard, and some line marking describing where the pedestrian ramp is going to be when this intersection comes together. Okay. So the first thing I'm going to build is, well, I'm going to start to build the Apply MTF function, because we need a bit of information before we can do anything, and that's what is the typical standard normal kind of shape and levels that we're going to have here with our curve and our verge and all that kind of thing. So the apply function itself is where things are different right from the very start. Okay, so on the front, that's all normal. We've selected our alignment string, got our team, etc., etc. But this is where it's different right from the go. In the Models tab, absolutely nothing in terms of strings and sections. So I'm going to use the create commands within the modifiers themselves to generate data where I need it, where you've got much more control when you use the modifiers than you have if you just let 12D create strings and sections for the entire function. Still creating the polygons though. They're quite handy when it comes to visualization time and so forth. Okay. Yeah, and that's basically it. The rest of the MTF is just completely empty. So if we go into the MTF itself and have a look at what's going on here with our commands, Oops, excuse me. So the first thing is just putting in a standard profile. Okay. So inserting a template, again, nothing particularly outrageous about the template. It's just shape of the curve, shape of the verge, making sure I'm still using my names and colours and so forth as you would normally. Okay. But remembering when I apply this, none of the strings and cross-sections are going to be created, but the calculations of applying this template still happen behind the scenes or in the running of the MTF. But what I am going to create straight up is a tin. So I'm taking all the information in my design layer, which is what my template has been added to, and creating a tin from that information. And over in my 3D view here, this is the tin that's being created from applying that basic template. Okay. Then just park that away for the moment because I will be coming back. There's a lot more work to do in that one yet. Now, the next sort of step along this journey is to create a few construction alignments. Okay? It's all very good to say, yep, you can use these computators and everything, but they've got to computate from something. So the first thing I'm going to build is a few construction alignments. The first one being a small alignment string just describing the center line of this ramp. Okay, because that center line is a critical one in terms of grades and sizes and so forth. And I'll bring up the editor for this one. Okay. Now the horizontal geometry is well, pretty basic really. Just drawing a line which is starting from a coordinate which is just the center line of the pedestrian crossing where it intersects the curb return alignment. With a little distance either side of that, just so that I've got a bit of room to move when trying to work out these grades. Now this is where things get a little bit more fun. In the long section here, for this construction string, doing a couple of slightly tricky things. Firstly, the 12.5%, because that was the maximum grade or the preferred grade for these curb ramps. So the first computator is saying that starting from, well, essentially our curb return, but from a construction, I'll come into this in just a second, but starting from the invert of the curb, coming up at 12.5%, and then, well, how far does that go? That's the big question. Where does this thing, 12.5%, actually end? I've dropped in another computator here purely so that we can pick up the proposed levels sitting in behind on the verge itself. And the way I've done this one, to make sure that I get an intersection, I did experiment with doing the, just doing like a drape, but because you're never 100% sure just where things are going to lie, sometimes it'll work, sometimes it wouldn't. So I've gone for this method of just drawing a line by 2 points, specifying a chainage so that I'm a distance back from the point there, but the height is coming from a tin, coming from that tin created by the MTF. Okay? So the first point, chainage and height from the tin. Second point, chainage just a bit further along, and again the height coming from the tin. So that way that line will always find an intersection with this other line for 12.5%. Okay. And yes, so I did accidentally just skip over one of my construction strings. I'll come back to that in a sec, or right now actually. So these other construction alignments here are simply running parallel to the curb return itself. So if I just open the key one here, which is running along the invert of the curb, it's two very simple computators just referencing the curb return itself at the offset to the invert. Now whether you do the entire string or just a segment, in this case I've done a segment because the alignment actually goes a little bit further west than just the curb return. And in the vertical is just a simple offset grade with a very tight interval I wanted to make sure that the levels that get calculated are as accurate as possible. Because if we start putting in the intervals too big, then you might not quite get the right levels where your construction centre line of the ramp actually intersects with that invert string. So really tight intervals is the key on that one. Probably could have even gone even smaller, but this seems to work okay around that point. You notice there's a few other parallel strings in here, so I've just replicated the top of curb and back of curb. They might come in handy later on. So while I was there, I just created all three of them basically. Okay. Now, coming back to the centre of our ramp itself, the critical thing in this string is using the named positions that are available in 12D. Now, I'll be perfectly frank and say I've never really found a great deal of use for named positions, but this is just absolutely perfect for the situation. Now, I've created two named positions. So that SDA was originally side A. I probably should have renamed that to center line, but when I first experimented with this, I was creating construction on the side. Anyway, not to worry. But I created a point at the invert and created a point at the top of a named part called SDA. So one at the start and one at the end of this named part. But the cool thing here is that that named part is in fact the vertical geometry. It's that vertical segment that's coming at 12.5%. So from the vertical geometry, I can establish some actual spatial positions, some X, Y, Z positions for the start and end of that bit of vertical geometry, which we're going to use in just a second now. So that's probably the second sort of kicker in terms of using things just a little bit differently. Okay? So how does that actually happen now? So if I put on the strings that I'm actually generating from this, now the first one that I'm going to construct as part of the actual finished product, the ramp itself, is just this line coming down one side of the ramp itself. Now, again, all fully computated, of course, so that everything's related to something else. The first point, nothing particularly mysterious about this one, but it's the intersection of our construction line down the middle here and our invert of curb. Okay. So our construction line with a 0.75 offset in this case, because I've got a 1.5 metre wide ramp, and the second string being the invert of curb. So we found that point easy enough. That's all great. It's this second point, which is the interesting one. Using the named position from our construction string up the centre line. So we're actually defining a horizontal point from the vertical point of that construction line, using these named positions as that link between the two. And that was probably the thing that actually makes this whole thing possible. So that's really a key point to remember. Using a named part on a construction, defining the start and end of that vertical with positions, and then we can use those positions in other computators, and in this case, a horizontal geometry computator. Okay. Now, in terms of the vertical geometry, very, very similar to the construction string in the first place, in as much as our first point is simply cutting through the invert level, that invert string. The second point, using this mode of complex again, saying the chainage is just the end of the horizontal geometry, which is perpendicular to that named position, and the height is just coming from our tin, from our apply function. Okay. So nowhere yet have I specified an actual coordinate or anything except for that original construction line. Everything else is fully computated. Okay. So once you've got that structure, everything now sort of starts to speed up a little bit, gets a bit easier, because the string running on the other side of the curb ramp is exactly the same. It's just that that offset is in the opposite direction to the first one. So to create this alignment in the first place, I simply went to strings edit duplicate, made an exact copy of that first side string, just gave it a new name, and then the only thing that was left to do was to come into the computators and just change the side of the initial intersection, that it was a positive offset instead of a negative one. And the endpoint is exactly the same as it was for the other one, so there was absolutely no change there, again, except for the offset. It's just heading in a different direction this time. Okay. And vertical geometry is absolutely identical. There's no change at all. Just cutting through the invert and dropping to the tin at that endpoint. Okay. Yeah. Then the last couple of strings, just to sort of finish off the ramp itself, well, the first one would be the one that actually wraps around the back and along these sort of wings, for want of a better word, where it transitions back up to the normal footpath height or curb height. Yeah. And even though that may sound interesting, it is literally just joining the dots. It is really quite simple. So the first point, again, using this idea of intersecting strings. So we've got intersections of backs of curves with intersection of that side with the 600 offset that's needed. Okay. So just intersecting those couple of strings with a bit of an offset and using exactly the same sort of name position or name part, depending on which way you want to go, for finding the endpoint of this little side string here. Now I've used name part referring to the side in this case, just the end of that string. A part that turned up relatively recently, I can't remember if it was version 11 or version 12 that this one turned up, a free connection. So it's not trying to make things tangential or try and find intersections or anything like that, simply joining one point to the next point. And in this case, joining through to the start of the next computator, which is going from the end of this side through to our intersections with a bit of offset describing that wing point. Okay. Looks complicated, but it's just joining dots, basically. Okay. And once again, the vertical geometry for this thing couldn't be simpler. I'm simply getting all the levels from that design tin. With one little trick though, I've ticked this little box here that says horizontal tangents only. So instead of giving heaps and heaps of IPs all the way along this thing, I'm just getting a level calculated at each of these 4 points. And if I was to show that into a long section, just to sort of demonstrate, it keeps it all nice and simple and straight lines. You haven't got lumps and bumps and things coming through into the final product. Nice clean lines. Okay. And just from the start to the end of the string. So vertical couldn't be simpler on that one. Okay. And that really is the actual curb ramp itself, almost finished apart from just one little thing. I did a lot of experiments trying to use modifiers within the MTF itself to transition curb heights and to take bits in and take bits out through the face of the ramp itself. In the end, I felt like I was just sort of wasting time because there's so many modifiers to make that happen. So what I've done instead is just throw in another 2 super-alignments. Okay. I'll just turn off the construction stuff. So it's getting a little bit busy, a little bit tricky to see here. But just threw in another 2 super alignments at each end just to describe that transition of the curb itself. So going from basically having no curb at all from this invert point, transitioning up to the full height and the full size of the curb. And again, really nothing particularly outrageous about the string itself. It's once again just simply joining dots. So the first point is just the start of this little back string through to the start of my side string here. And the last one, using a floating computator this time, to a point which drops perpendicular from the start of this back string onto the back curb itself. So finding that point was one I had to do a little bit of experimenting with before I got the right combination of things. But using that start point of the back of the ramp, dropping perpendicular to that reference being the top of curb, my construction top of curb alignment there. Okay. And again, vertical, nothing particularly outrageous, using the same philosophies as before, but using the strings that have been generated previously, just cutting through them, whatever the height is whatever it is. Okay. Getting it from tin if the cut didn't work. That was one thing I found actually, because this little wing was doing a major change in direction, hitting that point but not actually continuing through or cutting through, then I couldn't actually get the height from a cut. For some reason it didn't want to pick it up. But the tin, that curve tin from the imply function, is the same levels anyway. So within millimetre, it's pretty accurate. Okay. Right in vertical just to show what I'm talking about here. So the first line just going from the end of one string down to the tin level at the invert. A free line, because I found it a little bit tricky to define this endpoint as a float. So just like you would with a curb return alignment itself, I've used a change reference just to pick up the level of the top of curb at that end point, that third point of this little wing. Okay? But it's never really ever going to get used because it goes beyond the horizontal geometry anyway. Just using it to set this level for this free line to be able to join to. Yeah. There quite probably are other combinations that will work. That was just one that I came across that seemed to be quite reliable, so I stuck with it. Okay. And then just exactly the same thing on the other side, simply joining those 2 points at the end, dropping a perpendicular and getting the levels from either the other strings as a cut or from the tin as a drape for a specific point. Okay, and that actually is the ramp itself. That's all basically done. Okay. I'll just drop out of those. But as I said, I mean, one of the whole purposes with this thing was to get this fly-throughs and visualizations and all these kind of things right. And we know that in those early stages of the project, chances are something's going to change. That's why I went this whole computator method, so I can deal with those changes. Yeah. But we need to sort of build up the full picture now. Okay. So once again, sticking with the idea of using computated alignments, because I want something that can actually rebuild itself, I just had a bit of a dabble of maybe creating like a concrete hard stand around this thing, and even having the replicating what a concrete footpath coming up to that hard stands. Now this, I just sort of threw these together as an experiment and it kind of worked okay. Obviously every individual job is going to be a little bit different, So you just have to deal with whatever shapes you've got at the time. So these are a couple more alignments that I created just to try and finish the picture, so to speak. The first one, this one here, so just basically creating a platform or a hard stand that runs around the outside of the whole curb ramp itself. The idea being that we've got plenty of room to put tactile indicators, to put signal posts, pedestals, all that kind of stuff, all on a concrete surface. It seems to be the flavour of the month. So again, nothing absolutely mysterious about this, but it's just a case of working your way through and building up the picture, referencing all those strings that we've already created, with a few of them invisible because we simply don't need them in the finished product. So the first reference is using a back of curb, as you can see that's just been highlighted in red, so referencing that segment of the back of curb as an invisible, so that's purely really just there to find this intersection point more than anything else. Okay. And the next segment just running parallel to the back of that curb ramp itself. Another segment just running around at the limits of the concrete footpath and concrete platform, running parallel to the curb return itself. Coming back down the other side, just running parallel to the side of the curb ramp, with another invisible segment, essentially just to create that intersection. So I probably could have done this as finding intersection points of strings, but I found this method really quite simple. So it finds the intersection of that next segment, and because it's invisible, the string basically stops. Okay. Again, vertical geometry, simple as simply dropping it onto that tin that was created from the apply function in the first place. Okay. And the next couple of strings was the footpath itself. Now I've just gone parallel to the curb return here, but they could have gone in straight direction in line with the curb ramp or something. It all just comes down to what you need at the time. But whatever it is that you're trying to describe, it's all relationship based. It's all going to be relative to something. So you can use these computators of segment references and so forth to describe just exactly where the edges of your paths and verges and things are actually going to lie. It's all just a relationship to something. That's all about. And again, so simply just running parallel to the curb return as the first segment, second segment running parallel to that platform with a little bit of an offset. Now, I did go for that offset for a specific reason. When you've got strings exactly on top of strings and the points are not actually identical and segments identical, you can start to get some sort of crossing breakline problems coming through with your tin. It can start to look a little bit wonky. So I found that by having this tiny little offset in, it meant the tin creation process had no issues, no crossing breaklines, and everything worked okay. And quite frankly, let's face it, 1 millimetre is pretty hard to see out there in the real world. But anyway, so all these segments just running parallel to some sort of reference, whether it's the curb return or hard stand. And again, vertical, just simply dropping onto that tin that we created from the MTF. Okay, now heading back into the MTF to start to actually build up the final picture itself. Actually, before I do that, I might just prove that we have actually achieved something here. We've got our curb ramp, and we've got our hard stands and footpaths, and we've got the curb return itself. So everything's sort of starting to come together now in terms of an actual real object. Okay. Anyway, back into the MTF itself to start sort of finalising the rest of the model. Because remembering that the actual basic template has already been applied. It's already running. The entire shape has already been created. It's now just a case of picking and choosing which parts of that we want to turn into actual visible strings. So a couple of things I did here. Firstly, I just set up a chainage alias called ramp using these strings that we created of the ramp itself to just define the region where I really don't want to create any strings out of the original template. But everything outside that region, we most certainly can. And that's why the next bunch of commands here are simply create string commands. So I'm just going through and saying, just turn all these on. Could have done it globally, but it's only a few. So the whole idea is we're now saying that there are certain links from that template that I want to turn into a string for the entire length of this curve return. And those are the string running along the lip of the curve, the inverted curve, skipping all the stuff in the middle, so skipping the top of curves, back of curves, foot paths, all those kind of things, skipping them, going right out to the verge line, right out to the very edge and to the interface, to my batter. So they're the only parts of my template that I'm turning into visible real strings over the full length of the curve return. The next ones start and stop in different ranges. So the top of curve and my back of curve, I'm only creating from the start up to the start of the ramp, and then again from the end of the ramp through to the end of the job, the top of curve and back of curve. Okay? So just picking and choosing where I want to create these things. And the last one here was the footpath strings, turning them into real strings, actually beyond the extent of the curve return itself, because the alignment goes a bit further, so I was turning into actual strings down here, so really outside of the scope of what we're talking about. But it completed the picture. Okay. So when we apply that one now and turn the models on that came from that function, so as you can see here, the invert, the lip going all the way through, the top of curve and back of curve simply stopping where I don't need them because I've created all these alignments to create that shape. Okay. I find that a lot simpler than trying to do all these heights and widths and whatever modifiers, and you end up with all these links on top of each other and it just gets extremely messy. Or you start removing links anyway. So, and that was what actually gave me the clue. If I've got to remove all these things, why not just not create them in the first place? And it just made the whole process a lot simpler to get my head around, basically. Okay, so we're really now starting to get something which is a much more complete picture. Then I hit another slight quandary. What do I do with my boxing? Because normally when we're applying boxing, even using Peter Taten's awesome snippets to create all those models, it's all very well where you've actually got all the strings that describe the curve, but I don't have those strings in here. They stop. I've got no back of curve, I've got no top of curve. So I had to just think about what to do with that, and I came to the conclusion that I just needed to create another pavement style. Because the original pavement style came out, actually, I can't remember which one it was now. Sorry, I pulled this from another job, so it's a bit, a lot more pavement styles in there than what I actually need, so bear with me just one second. Okay, so style 1, zone 1. Alright, that's pretty straightforward. I think I can live with that. So style 1, zone 1. So with my normal curve profile, we're dealing with an offset for the lower layers that goes out 150 behind the curve. That's normal, typical kind of offset behind the curve. So that's going to put me out here somewhere. But where I don't have a backer curve, that would then step me back in, which doesn't quite work very well. So we're just really lucky, or Peter had awesome foresight to be able to allow us to only use 2 links in his pavement snippet if we had a curve that was literally only described by 2 links, which is what I've got here across the curve ramp. Okay? So it was just a case of just tweaking the style just a little bit. So everything about this pavement is exactly the same as the first one. The only difference here is a slightly greater offset that happens behind. Whoops, sorry. Must have closed that by mistake. Apologies for that. So slightly different offset behind the curve this time, just to make up for that difference in width from the full curve to this cut down one where, whoops, where am I? Yeah. So because this curve is actually 150 mils smaller than the standard one, I just increased my offset behind the curve by 150 just to compensate for that slight difference. Okay? So what that means now is just using the curve snippets that we've seen plenty of videos on before, which is fantastic. By having those 2 styles, we've now got, what have we got? We've now got the curves being created where we've got full curve, just the simple curve from the lip to invert being created where the curve ramp sort of takes over from that point, but the pavement materials continue right through the same size just by adding that extra 150 mil to the offset. And we really are now starting to get this thing well and truly under control. We've got surface strings built, we've got our boxing, our tri-meshes built. The last thing to just really complete the picture is to be able to generate a tin that we can use in a visualization for fly-throughs and so forth. Okay. So the biggest problem with that is having the polygons that you need to show the different surface treatments, the different materials. And because all these things are potentially going to change, then I didn't see any way out of it except to create those visualization polygons using computated super-alignments. Okay? Now they are essentially just duplicating all these things. So quite a number of them I simply duplicated the string and tweaked it a little bit. These ramp polys, here we go. So, and here's an example. So this is probably the hardest one of the lot because it does sneaky little changes of direction here. But all the other ones are just simply duplicating and just closing off instead of leaving it open as I've done here with these ones. So editing this visualization polygon here, again, it's just segment references coming at your ears almost. There's plenty of them, but there is a simple logic. You simply work your way around referencing that segment, referencing the next segment, referencing the next segment, referencing the segment along the back of the curve there, referencing the segment of my little transition, this little wing transition here. Oops, zoom in a bit so it's a bit clearer. Just referencing that segment, referencing the invert. I did hit a bit of a brick wall here. Simply going to a segment reference actually failed on me. Something to do with it, the way it's changing direction. So I'm not quite sure what it was. So I just threw a little tiny little radius in there just so that allowed 12D to calculate where all these things meet. So that's a little trick for you. If you ever are doing a couple of segment references and for some reason it just refuses to find that intersection, just throw in a little free arc and it'll be quite happy. Segment reference again on that little wing alignment there. Segment reference along the back of the curve again. And of course the sneaky little trick here is to make sure that it is in fact closed so that it finds the intersection of those two segments back at the start point. So a visualization polygon, which is purely and totally computated from the strings that you use to generate the ramps, the curbs and the hard stand itself. And there's plenty more of them. So there's computated alignments all over the place, as well as the visualization polys that came from the apply function itself, because I did ask it to create those polygons. Okay. So because we want all this to be repeatable, the clue, or the absolute critical key to this whole thing, is making sure it all gets added into a chain so that you can, well, repeat the process basically, but also know just how you actually created all these strings, in what order, so forth and so on. And right down the very end here, so after all the resolving and the super alignments, we get to the point where we can in fact build a tin from all this data. So I've got a tin which is a combination of the alignments that we use to build the curb ramp, the alignments that I use to build this sort of hard stand, and the strings that came from the apply function. A couple of little screen layout files I've just captured just to colour the tin. The trick is to make sure you do this in the right order, of course, because we do actually have some overlapping polygons here. So the first time it runs the colouring, it's just using the ones from the apply function, just heading straight through. The second one is using this extra polygon that I created over that concrete area, over that hard stand area. Okay. So when that all gets run, which doesn't take all that long, we end up with a tin that has all the basic components that you need essentially. We've got some grass, we've got some concrete, we've got the ramp happening in the middle. Basically something you could actually use in a proper visualization. Now the whole point of all this was so that if something changes we can just tell this chain to go and rebuild everything. So just to show a little example of how that may happen, I'm just going to put my construction string back on here for a second. I'm going to edit this one. And I've got a different version of horizontal geometry. So my first version is here, the one that we've been using. I'm going to turn that one off. The next version is moved along the curve a little bit, as well as a change in direction. Okay, so maybe not the biggest change you've ever had to come across, but still a substantial change in its own right. Okay, so if I just drop out of there and rerun my chain, all those strings can now rebuild themselves. Admittedly, I might have to have a bit of a rethink about exactly how I created that platform, but you get the general idea. The curb ramp itself is all reconstructed nicely, and even the tin, the visualization, the boxing, everything has been reconstructed to match that new alignment and that new position. Okay. And that is the whole thing in a nutshell. So, yeah, back to you, Lisa.
Thanks, Dave. I think that was pretty comprehensive. We didn't have a lot of questions through, but there was one early on I'll just read out in case it still applies. I'm just not sure whether it's been covered later in the presentation or if it's too hard to go back to. But Ed in Sydney was asking whether you could have used the Apply MTF string for the invert.
No, the reason why I can't use that in computators is because every time you apply the function, that original string has been deleted and a new one created, and the computator breaks because the string that you were computating from doesn't exist anymore.
Sure.
So that's why I found it's much more robust, put it that way, to create these little super alignments which are basically replicating that curve shape because they're stable. They stay in that position. And because they're computated, if I change the curve return itself, position, grading, whatever, they're all just relative to it, so they'll all move with it.
Okay, great. Well, thank you, David. We've got some great training courses coming up in person in Brisbane, Melbourne and Perth. I think we've got a bit of a slide showing just some of those, but yeah, there's lots more information on our website, and you can contact us by email for more information. And our big event, of course, is our 12D Technical Forum on again in Brisbane this July. It's already got lots of people registered. It's going to be pretty huge, but please jump online and register for that if you haven't already. The recording of today's webinar will be available in coming days through our website and our YouTube channel. Our next two training webinars are Precise Culvert Length and Location with Drainage Strings on the 23rd of May, which is tomorrow actually. And I think the next one after that is in June, so then we'll have a little break in the lead up to the technical forum because we'll have enough on our plates at this point, I think. We'll keep you posted on all of that through email and social media if you're subscribed, and if you need to contact us in the meantime, our details are on the screen now. That concludes our presentation for today. Thank you all for attending, and we hope to see you at future webinars.